Pessoal, boa tarde. Sejam bem-vindos aqui ao Colóquio do Instituto de Física. E para apresentar nosso convidado de hoje, né, eu chamei a professora Márcia Risuto para ela fazer a apresentação, que acho que tem tudo a ver com o tema de hoje. Márcia.
Obrigada. Obrigada a todos pela presença, né? Nesse colóquio de hoje, nós vamos receber o professor Koen Janssens. Ele é professor titular lá na Universidade de Antwerp, na Bélgica. Ele é responsável pelos cursos, né, no Instituto de Física, dos cursos de Química Analítica, parte toda de análises instrumentais e raio-x para uso de caracterização de materiais. Ele obteve o PhD dele em Química Analítica em 1989, e, desde aquela época, ele tem trabalhado ativamente com o uso de feixes de raio-x, né, ou feixes microfocados para usar para análise de materiais. Trabalha bastante também com Synchrotron, né, sempre numa tentativa de análise de materiais de modos não destrutivo, que, para a área de patrimônio cultural, é muito importante você usar essas técnicas que você não destrói a amostra, né? Ninguém quer destruir uma pintura da Mona Lisa, por exemplo, né? Então, a ideia é usar todas umas técnicas analíticas para a caracterização de objetos do patrimônio cultural. Então, ele tem grande experiência, né, nesses estudos, e ele também trabalha numa área de degradação de materiais de patrimônio, né? Então, buscando também entender os aqui, isso. Então, voltando um pouquinho, ele sempre está trabalhando também com essa parte de degradação de materiais voltado à área de patrimônio cultural, né? Então, ele é coautor de mais de 400 artigos científicos, então, com uma produção muito grande, né? E ele é editor e coeditor de várias revistas científicas do meio, né? Sempre trabalhando com técnicas não destrutivas. Então, thank you very much for accepting us to stay with us here, and it's a pleasure to have you here. Thank you.
So, I hope everyone hears me with my small microphone. So, thank you to the Institute, and thank you to Marcia for the invitation and for the opportunity to talk to you a little bit. We're going to talk about the analysis of paintings, and myself, I think Marcia explained this already. My training is chemist. I teach to chemists, but also to physics students and to bioengineers. And occasionally I also teach to art conservators. And in our research group in Antwerp, we have all these people in there. We have physicists and programmers and engineers and chemists and an occasional bioengineer, but we also have art conservators. And all the way on the other end, we also have a few art historians. And so we try to collaborate and help each other with different expertises and arrive at a higher result than all these people separately would be able to achieve. So this is going to be a little bit of an eclectic talk, and I hope you will like this. Yeah, this here is a bit advertisement. It's obligatory advertisement for the sponsors. So, yeah, it's there. I've shown it. When I first started working with paintings, anymore like they used to look when the artist was painting them. So a very well-known example here is the sunflower painting by Vincent van Gogh. It dates to 1888. But the general belief at the time was, and still is, that a number of these yellows look much more brown than Van Gogh intended them to be. Yeah? And so this is a problem of durability, you could say, a generic problem. Artworks that are not so durable. Of course, they were not meant to be so durable. Van Gogh did not know anything about the durability of the materials he was painting with. He had a hunch. After 10 years, he also started noticing that, oh, this type of yellow starts to darken. Maybe I should use another yellow for the next 10 years or something like that. And of course, this was then in the framework of art. And so we started investigating that with some methods available to us. And I thought, yeah, these three would come to a useful addition. But it turned out by doing that, that actually a number of fields showed up, extra fields, because we started to see things that also art historians thought relevant. And what we were doing then, when we were looking or discovering this new information below the surface, was not what did not really have too much to do with changes in color at the surface, but what was below the surface. So we were digging below the surface without really disturbing the painting, because we were using non-destructive methods. And so at some point I found out we were doing a form of archaeology, going back in time, but virtually, because we were using penetrative radiation to get to that information. I'll show you a few examples. So this was interesting. This boiled down that the non-destructive part of the methods was more interesting than the other part, and that you could do this for different purposes and interest or raise the interest of different kinds of people. And that's, of course, always interesting as a scientist, to be able to help others. All right, so now I said we were going to speak about paintings. Let's remind ourselves why paintings are so interesting. Why everywhere in the world, especially now everywhere in the world, maybe a little bit less in Asia, paintings are, a lot of money is spent into creating buildings and organizations that preserve paintings. Why do we do that? Why don't we just throw them away if they're so difficult to keep in their state? We can take a picture and forget about the original. We don't do that. Well, first of all, because paintings, as it said there, are credible windows into the past. What you see here is a fresco. You can go to Pompeii in Italy and look at this fresco in the Villa of the Mysteries, and you will get immediately an idea on how the Romans lived. Maybe not all Romans, high-level Romans, but you get an idea. This is 2,000 years ago, how people lived. Without these paintings, we would not be able to imagine this in a fairly accurate way. All right, so that's one reason. What you see here is Clara Serena Rubens, the daughter of Rubens. Rubens is a 17th century painter from my city, Antwerp, in Belgium. And he loved his daughter, especially when she was young and looked so innocent. And what you see there is the master painter who tries to catch, by using a Polaroid, 17th century Polaroid, how his daughter looked before she became a mother herself and looked much more tired because when she was still fresh. And Rubens could paint his daughter this way. Now we can more or less all do that with our phones, but in the 17th century this was not so. You had to have great skill to create this realistic image. And therefore, these kind of images are rare, they're difficult to make, and they get value because of this, and therefore we do a lot of effort to preserve them. Okay, that's clear. Mostly in what I call Western culture, Asians tend to not agree too much with that, but okay, they're also adapting. All right, another reason, here is another quite different painting. This is a painting by Van Gogh called the Irises. Wonderful colors, very intense. You can admire this in the Paul J. Getty Museum in Los Angeles. Very nice. Why is this important? Yeah, because it's beautiful, and you can also admire the subtle play of colors, etc. Van Gogh, his painting techniques, but most people just say, oh, what a beautiful painting, all these colors together. That's also a very simple but important reason. All right. So how do painters like Rubens or Van Gogh work? Yeah, in a very complicated way without showing that. And this complication is revealed when you do not just look at the paintings XY, but in Z, in the Dept, because to get certain effects, you need many layers on top of each other, and each layer is rather complicated in structure. It's not a homogeneous material. These are usually one or more colored small particles held together by something called a glue. We call this a bit more refined binding medium, oil, sugar, something that keeps for ages all these pigment particles together and in layers. Yeah? So we have pigments, usually inorganic. We have dyes, which are also colored, but are organic. And we have then some organic binding medium. Yeah? And all these layers, only here a few are shown, 1, 2, are usually on top of a ground layer and then on the material which is really the substrate of the painting, canvas or panel or something else. But in reality, actually, these layers, and especially with the complicated high-level painters, there may be 5, there may be 10, there may be 15 layers on top of each other, with different transparency and thickness and color and heterogeneity. So this is a complicated business to read that and to extract information from that. Okay, so you see this here. You have these layers and layers. And so, of course, to analyze that, what you need are microbeam methods of different kinds so that you can focus on one layer and extract some information on that. And hopefully you can do this in a non-destructive manner. So in Dept, you need a length scale which is on the micron level or lower, because you could also imagine that when you look at the interface between two layers, all kinds of things are happening there. You may need a nanometer level method. If you want to just look at the layers in their totality, you need a micron level method. And then there is the painting as a whole, and then you need the resolution in the millimeter level to understand that and create images. So that also is a bit complicated, but nevertheless not impossible to realize. Okay. So again, when we started about 15 years ago with this paintings characterization methods, I knew that, of course, you could take very small paint samples if the museum people allowed you to do that, which is not very often the case, and do regular microscopy and electron microscopy and all kinds of techniques on that in the lab. But when you wanted to have the full characterization, the macro level characterization, the traditional tools were limited. And one of these traditional tools that all the museum in the world use is X-ray radiography, which is a crude method of saying, let me first explain. Here there is a painting you can admire in the Prado in Madrid. It's called The Garden of Earthly Delights by Bosch, which is a 16th century painter. And it's a little bit busy painting. Left you see heaven, where it's relatively quiet. In the middle you have the earth with all kinds of profane activities I'm not going to talk about. A lot of symbols in there. And then on the right you have hell, and there's a lot of activity in hell. There's a lot of sinners who are being punished, and that kind of things. And of course, that is the panel that creates the attention. You see here somewhere in the middle the Styx, the river that goes through hell. And we're going to focus here on this little man in the boat on the Styx. So here is the panel of hell. And as I was saying, radiography, X-ray radiography is the method of standard choice, which is done by putting, let's say, this panel, for instance, on a table, putting an X-ray tube that shines upward. Then on top of the work of art, you put photographic films. You expose it, and then you put them all together, and then you get this radiograph. And then you know what you're doing is a kind of absorbance imaging. In every pixel, you measure the absorbance of the X-rays, and where you don't have a lot of blackening, like here, this monster that is crawling out of the river, there the X-rays were strongly absorbed, and you can see something. So here we see our little man in the boat again. Here he is, but this monster here was painted before with a strongly absorbing paint, probably containing a lot of lead. We don't see that anymore. Bosch changed his mind, wanted to have something else, so overpainted that. That's the reason why all the museums in the world use this X-ray radiography. But the only thing you can really see there is the contrast between areas containing a lot of lead, strongly absorbing atom, and not so much lead. It's very simple. For instance, here, and you have this flute, this brown colored flute with a little arm sticking out. If you look carefully, you see this little arm here, because it's painted with lead white, but the flute is not there. It's there. You can see it with your own eyes, but it doesn't absorb a lot of X-rays, so you don't see it in the radiography. So if there was something painted with a brown paint or another material that doesn't absorb, you will not see it in the radiography. Okay. Radiographies are black and white, kind of symbol for saying, well, we give you one type of information, but certainly not a very rich type of information. So, yeah, you can see this here. I should have explained on here. You see a little bit better the little arm sticking out there, but we see it. So actually, what I sometimes compare this to is like when you have a family and you have an image of their bones, you can see the major stuff. You see that there is a father and a mother and 2 children, but the rest of the information is not there. And actually, that's what medical people do when they use X-ray radiography. So we tried then to do something else to create an equivalent of this, but spectroscopically richer. For instance, to look at different atomic species and how their distribution was. And yeah, this was our first successive experiment. As you see myself much younger than today, in 2007. But very happy also, as you can see, and I'm still happy. All kinds of other people were happy there too. And the reason why is that we convinced this lady here, which is a Dutch curator, to bring a small Van Gogh painting to the synchrotron beamline there in Hamburg, which, if I think about it, was sort of impossible to do, but we tried and we succeeded. And this was a small Van Gogh, very colorful, called Patch of Grass. And what we were doing is we were shooting with an X-ray beam of relatively high energy, 40 kiloelectron volt energy on the painting. Of course, not the way you see it here. We were doing that while all the people were outside of the hutch. But okay, that was the point. And the painting was on a moving stage, so we could do a scan, an XY scan, and collect then at each position, this kind of serpentine scan, collect information via X-ray fluorescence, and to our great surprise, something completely different than what you see on the surface came out. All right, so, and why do we see this? Because Van Gogh was so kind to paint below this landscape with all these flowers, to use 2 pigments, antimony and mercury, which give this contrast, and you can clearly see then what he painted, this kind of portrait. Okay. So here is our curator again, placing with gloves, etc., her small Van Gogh in the beamline. So what we were doing is, when she was gone, hitting it with a beam of small dimensions, but not terribly small, 0.3 by 0.3 millimeter, and then collecting X-ray fluorescence. And in X-ray fluorescence spectra collected from each point, you can see which elements are present on that location. If you extract from each pixel the intensity of the element and reorganize everything into maps, then you get, for instance, here the chromium and the copper maps from the area that we were scanning here. And if you look at these maps, it's nice to know that there is chromium and copper, and you can guess at which pigments are there, but it doesn't really provide you too much new information because it's all the colors which Van Gogh used on the surface. But, of course, by looking at the mercury image and the antimony image, this is certainly not the case. And so then we could combine these, and then if you let some computer specialist work on that, remove some of the artifacts, you get a clearer picture there. All right. So this was the start of an adventure of which we don't really see the end yet, the Macro-XRF adventure. Because we then did another move, which was not bad. And while we did these first experiments at the synchrotron, thinking, oh, we will need this high energy and high intensity to have something that we can use easily, turned out that by downscaling, by keeping the principle but downscaling the X-ray source, it could still work. Yeah? So we built a scanner by using more or less the same stages than at the synchrotron, but with an X-ray tube that moved. And then what we also did was convince a company called Brücker in Berlin to make a little bit more sturdy, a bit more reliably working instrument that people could buy. Yeah? And one of our first examples was in the Rijksmuseum in Amsterdam, where we took our self-built scanner too. You see here this Goya portrait. Goya is a Spanish painter of the 18th century, I think. This portrait is very valuable, and the Rijksmuseum would never, ever have allowed it to go to a synchrotron, which is a dangerous place where you can burn material easily. But they allowed us to come with our scanner, and they could keep watch on what we were doing, etc. And so by combining then the same elements actually as in the Van Gogh portrait, antimony and mercury, but now also with lead and iron, we could reconstruct that below this civilian portrait, there is a general sitting in a chair. The civilian is standing, he is a judge, but below is another portrait with a fairly high-ranking general, and there is a little tiny patch of red here, which we didn't know what it meant, but afterwards turned out that this is a very high-level order. And this is actually a portrait of the brother of Napoleon Bonaparte, Joseph Bonaparte, who was made king of Spain by his brother, while the other one was emperor of France. Okay. But the king of Spain left his throne, had to leave his throne when the emperor of France fell from his throne. And then all these portraits made by Goya of this previous age, they need to be recycled because they were no longer in demand. Were more embarrassment. So he overpainted this with another portrait here of this civilian. Okay. So that worked out very well. And actually, around 2015, we were going around Europe, scanning all kinds of things. Modern paintings, here a lot of Van Goghs, as you see. Paintings from the 17th century, a lot of Rembrandts, and also from the 15th century, and some more. So that turned out to be quite successful. I'll show you a few examples. And what I thought really interesting is that by doing all this scanning, as I said in the beginning, we started to extract information that was relevant for different kinds of people. So you can extract information on which is relevant for art historians, on how the artist worked and what he did in which sequence. That's this example of this flower piece that was overpainted. Then there are owners of artworks. They don't care on what the artist was thinking when he made it. They want to know, is it a real this or that? Is it a real Rubens? Is it a real Van Gogh? Or is it doubtful? Can I convince this? Can I have a letter from a professor saying, I tell you that this is authentic? And of course, there are art dealers that want the same thing. And then there are conservators and curators in museum that are not specifically so interested in the past, but more in the future of the paintings. What's going to happen in 10 years with my painting? Is the paint stable? Are the reasons that we do not see visually, but are there that will cause it to deteriorate? And things like that. Yeah? So that's interesting if you have different classes of customers, let's say. And so one of them I will show you here. It's a simple example. You see here this painting with two haystacks. And you see here also in this painting this ladder, which is standing against this haystack. And it's painted with some light blue pigment, and there is a red shades on there. Okay, I'll come back to these red shades later on. So it came to us from an art dealer who wanted to know, can you scan it, and please let us know whether you find the same things as in a real Van Gogh painting. Yeah? And no, it was not an art dealer. The question came originally from the Van Gogh Museum in Amsterdam, who wanted to know where do you place it? How close to real Van Goghs? Okay. And the reason what they wanted to know is that this painting sort of resembles an accepted painting by Van Gogh called Haystacks in Provence, where you see the two similar haystacks, but from a slightly different angle. This little shed here, which is here, is now on the other side. Which is possible. It could be that Van Gogh made a painting one day, and the second day came back and said, oh, I'll make another one. But now I put my easel a little bit closer or further away. Yeah, that's possible. But Van Gogh didn't really do that. He usually was happy to just make one painting in one location. But of course, he did make copies of some of his paintings. All right, and then here's another haystacky kind of painting, another yellow patch and blue sky and green, etc. And this we analyzed. This one was not available to us, but this we analyzed already before this came to us. So this is a real Van Gogh. And what you see in there is that, yeah, in this haystack, there is a lot of lead there, and there is some chromium. And lead and chromium together suggest us a yellow pigment, lead chromate, chrome yellow. We use that a lot. Yeah. What you see also here is arsenic and copper together in some green. And there is more green here in some areas, like here, this darker green. Not related to anything else. This could be chromium oxide, which is viridian green. Okay. And so the arsenic and the copper are together in one compound called emerald green. And so, and then there is zinc oxide in the white part. And all these things are very much into the regular palette, the number of pigments that Van Gogh used. So all these things you can find in other paintings by Van Gogh. Yeah? For instance, a well-known painting by Van Gogh we already talked about here, the Sunflowers, shows you a lot of lead chromate, zinc white in the lighter background, and our emerald green. And what you don't see at all, except for some retouches, is another kind of green, which is cadmium sulfide. Yeah? Here in this one, also not that much, some retouches, but actually not a lot. Okay? These are two real accepted Van Goghs. Fine. So then we started scanning with our mobile setup, but now in our cellar in Antwerp, this painting, upper half. And then we were looking at this part, and then you see there is a lot of chromium. Okay, fine. Van Gogh uses chromium compounds in the green, so a lot of iridium maybe, but no emerald green. Is possible. Then a lot of cadmium, yeah? And where is the cadmium in? In the yellow. Is that absolutely impossible? No, but we would have expected for this kind of bright yellow to also find some chromium. So first step on, maybe this is not really as it should be for that period. But yeah, a lot of cadmium yellow. And then what was interesting was that there was selenium in there. And selenium is in this red part here, and also in the lines painted, and also on these ladders I was showing you. Yeah? So selenium and cadmium together is of course possible. You have cadmium selenide, which is red. It's very possible, or that's what causes this red color. Cadmium red, fine. Maybe some solid solution, cadmium selenide and cadmium sulfide. The trouble is, and that's in this ladder, so it's not added, it's really part of the painting. The trouble is with cadmium red, it only became commercially available to artists somewhere in the 1920s, 1919, and then Van Gogh already died 25 years ago. So this was a kind of smoking gun, like, that's not possible. That's not a Van Gogh. So we could dare tell the Van Gogh Museum, don't accept this for this specific reason. Yeah? We did not hear anything at all about this afterwards. So this painting disappeared somewhere. It's not going to be a Van Gogh, that's for sure. Then, more or less in the same period, we also did something else, the inverse operation. Yeah? So you see us here around the painting, with people from different musea in Holland, And this is a big flower piece, not terribly beautiful, not terribly Van Gogh-esque. And yeah, this had a kind of strange history. And so from 1910 to 2003, so almost the entire 20th century, it was considered to be a little bit odd, but a real Van Gogh. And then somebody came along and said, no, 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 I don't like this, and wrote a catalog saying, this is Circle of Van Gogh or whatever, but not a Van Gogh. And then, yeah, there were some doubts whether this was true, this demotion. And then so they came to us and they asked, can you scan this? And maybe something comes out where we can sort of revise the demotion. So do a promotion, again, a repromotion. All right. This turned out to be a little bit more difficult to do than we expected, in the sense that when we scanned this painting from the front, all kinds of things came out, but nothing that was really very, very conclusive. All kinds of regular pigments, but not only for Van Gogh, also for all kinds of contemporaries of him. But as you can see here in this X-ray radiograph, below this flower piece, there is a scene there. There are two people standing there. And it was never very clear what they were doing. There were two people there because of the overlap of the paint on top. Yeah? So what we did to clarify this was to scan this on the back side. Not the front, because the front was covered with all this paint. Irradiate from the back side and use many detectors, 3 or 4, here, and then one from the real front, to get an image from the back side. And this zinc image here was very clear. You see better what is there. You see that this man, somebody is sort of pushing him, giving him, touching him like this, but they're not really fighting, these two people, they're in a pose. Yeah? And they're holding more or less each other's hand to remain in that pose. Yeah? And so people familiar with these things said, oh, this is a standard academic pose. And where did Van Gogh paint this? He painted it in my hometown in Antwerp because he was there for a few months learning how to paint like the Antwerp painters. And he describes this. So Van Gogh starts his career in Holland, then comes to Antwerp, then goes to Paris, then goes to Provence. And it's here that he starts to get some new ideas, let's say, but not a lot yet. So actually by clarifying this, and also by, for instance, looking at these hands that are keeping, these two people are keeping themselves in the pose, you see all this mercury, which is red here, and is red in reality. This is very similar to how some traditional Antwerp painters were painting shades, like Rubens and Jordaens. They were painting this with red. Not because there was red blood or anything like that, it's just a way of, traditional way of painting shadows. And apparently Van Gogh was imitating that. That's one. And then, of course, we uncovered, by looking here at the barium image, this kind of very sketchy way of painting that is very similar to accepted Van Goghs. Yeah? And so we found several indications that the lower portrait, the wrestling scene, the two men that were holding each other, was from Van Gogh. And so, yeah, this sort of split or changed the balance back from not a Van Gogh back to a Van Gogh. Okay, everyone happy, and especially the owners, one of the musea in the north of Holland, then reacquired their Van Gogh. Yeah? And Der Spiegel, which is a magazine in Germany in 2012, put that among then a number of images, important images of that year of science. Okay, it's a long time ago. Hola. So this was peaking below the surface. I have another example. Maybe it's a bit too much, but I like to talk about this because it's from another century and it's sort of fun to talk about this. What you see here is a painting by Rembrandt, which is on first look not terribly interesting. It's called the Syndics, but art historians like this very much. Rembrandt scholars like this very much, because when you compare that to other paintings where there are a lot of people in the 17th century, there is a lot of dynamism in this painting. And these people are sitting around the table and they're about to do something. It's a Polaroid. Yeah? While a number of other paintings, big paintings of that century, there are just people sitting They will never move again. They sit there already for 500 years. But here, yeah, there is dynamism. Of course, before we scanned this, there was the radiography. And you see it's more complicated. There are more figures there than you see now. So there is stuff going on, but yeah, you have these shades and all kinds of things that obscure the view. And then we had our LED LMAP by Macro-XRF, and this was somewhat clearer. And now you have to follow. We're going to talk about this person here. So these 5 people, they are the important people. These are the people that were part of this society, inspecting the cloth, and this is their servant. And apparently Rembrandt tried out different ways of putting the servant somewhere in the scene. So what did he do? This is our servant. First he put them here, okay, on the side. That's normal for a servant. They're not, but he didn't like that, so he moved them over there. But of course you see some shade here, some patch, but that's not the final position. He was moved over there, looking a bit to the side, yeah. But of course here it's not there. Finally he ended up in the middle, fine. If this one is here, then that character who is now there, who was originally here, had to be moved, otherwise they were too close. All right, another shift. What else? This one, who is now sort of leaning forward, originally was here and was moved closer to increase the dynamism. Yeah? So you see all kinds of things in the past of this painting. For Rembrandt, this is a late Rembrandt. This is close to his death. So here you would assume that the late Rembrandt just paints directly, freshly. No, this was a hesitant, older man who tried different things out and overpainted again. Some other details which you may not see very clearly is that all these people have fairly long hats, because that was the fashion. This one has not such a long hat. It had to be reduced to make room for this face. Anyhow. So art historians like this, because they can reconstruct, imagine what Rembrandt was doing. Of course you have other questions, like this one here. This is a 16th century painting from the museum in Antwerp. You see there a lady doing something rather unconventional. She just cut off the head of somebody else. So this is Judith, and she's holding the head of Holofernes. It's a scene from the Bible. Judith is a Judean, how shall I say? She's a hero, a female hero. And Holofernes was a commander of an invading force in Judea. So what she said was, I will go into his tent, cut off his head, and that will be it, this invasion. And this is what's shown here. So all kinds of representations of that. Sometimes a bit more discreet, and sometimes very, very clear what's happening. So this is Judith, and when we look at the LED image here, you see more clearly that she is in Holofernes' tent. This is the tent. Here in this blackened, darkened background, you don't see that very well. And what's interesting here is the cobalt map. The cobalt is a bit in the sky. Cobalt is in blue pigment, so that's not illogical. Here we don't see any blue anymore, but originally this was, of course, blue. Why is that? Because cobalt in a pigment, there is a pigment called smalt, which is a cobalt containing glass. So cobalt is there in an octahedral environment. There are 4 oxygens around cobalt. Then you have a certain split. It's not octahedral, it's tetrahedral. A tetrahedral split of the D levels of cobalt, and they absorb so that you get a blue color. Okay. But if the glass, and so a lot of use of this blue for tiles, in all kinds of historic periods, everyone knows this. But if this glass starts taking up water molecules very slowly, the tetrahedral environment of the cobalt changes into an octahedral environment, and the tetrahedral split becomes an octahedral split. And this means that instead of absorbing somewhere in the visual, absorbing red radiation to get blue. It shifts to the UV, and the color is gone. Yeah? That's what's happening here. And that makes the color go away. So what we can now do is say, well, we are going to give Judith her blue skirt back. Huh? We can do this a little bit strong or a bit less strong. And we can combine some other colors. We can say, well, the red here, or where there is a lot of iron, like we color it a little bit red. Where there is a lot of copper, like in this background, we color it a bit green. And then we use this blue a bit more damped to give an indication. So this is what we call virtual reconstruction. People visiting musea like this, but because you can put this next to it and they can say, oh, it looked like this, perhaps. They get an idea. They get an idea. And also restorers, art restorers, find this useful to sort of understand better what the artist wanted to do. Well, it's not correct in a quantitative way. It's correct in a qualitative way. It's better than nothing. Yeah? And it's certainly more rich than this dark composition. Yeah? All right. So that's another way of doing things. I don't know how far I am with time. Let me see. Yeah. I will go through this one a bit more quickly. What you see here is Jan van Eyck. Jan van Eyck is called the father of painting, of modern painting. He was a 15th century painter who realized that with oil paint, you could paint very realistically. Before him, a lot of painting was done with tempera paint, which is made with pigment particles and egg white or egg yolk. And you can paint a little bit, and then the paint is dry. You cannot really manipulate the paint very well. He said, by using oil as a binding medium, things go very much slower. Nevertheless, the paint stays where I want it to be, but I can still change. He could paint himself in a very realistic way, as you can see here. And his masterwork is this Ghent Altarpiece, which is a polyptych with a number of very detailed painted figures. And what I will show you here is what you see when this polyptych is closed. Then you see, for instance, here the two paintings of the people that paid Van Eyck to make it for their chapel, their grave chapel. So again, this is radiography. These wooden panels, they have a kind of lattice work on the back, which doesn't help the radiography. You see the lattice work, but not much else. So a very simple way of improving on that is just to use the LED image, then you see a bit better what has been done. And then, of course, with Micro-XRF, you have all these other elements, maps, that have a specific information on their own. But as I said, we're going to look at the donor portraits here. You see it before and after restoration. That was the original idea of the restoration, to just remove this yellow layer and to have a more fresh, more clear picture. But then the restorers started to see, when they removed a little bit of the red coat here of this lady, that below the upper red coat was another red coat, which was not so logical. Normally you have this one expensive pigment used. Why would there be another red coat below the top red coat? And they did this in several places, and this was almost everywhere. And so then they asked us, well, what can you tell us about this lower layer? So they were starting to suspect that this lower layer was actually the original layer by Van Eyck in the 15th century, whereas the top one was added later. And then they came to the conclusion, if we could be certain that this lower layer is sort of more or less intact, then we can remove the upper layer and again reveal the original Van Eyck layer. So this was big discussion, but they really wanted to know how much is still there. Is it 10%? Is it 50%? Is it 90%? And they said, well, if it's around 90%, well, we can start removing, because then we have almost everything. All right, so what happened? We were scanning, and then we noticed in this window here, which revealed the lower layer, where they removed partially the upper layer, we did not see that in the copper image. You see here the copper in the green. That's fairly normal. Copper pigments are green. There's a lot of copper there. But there is also a lot of copper where we did not expect it in this red rope. Why was it there? We don't know. But we did see that in the lower layer, there was no copper. So that there was a very clear difference in chemical composition between this upper layer and the lower layer. Yeah? So that was one thing that showed that there was a quite different, big difference. Yeah, some other indications. This was a big indication. And then in the other donor portrait, we could sort of see through the upper layer. This is very bright red. There's a lot of mercury in there from mercury sulfide. But below in the iron image, we could see where this lower layer had been repaired before the upper layer was added. So we could just see through, and we could sort of estimate how much area the repairs were taking up. And this was about 5 to 10%, but not more than that. Yeah? So with that information, you see it here a bit better, where you have less mercury, you have more of this iron-rich filling material from below, which you don't see visually, but see that contrast. With that information, and then with some cross-sections where you see these two layers very separately, this was actually enough to convince the restorers to start removing with some confidence this upper layer. And this turned out that these two portraits were actually very heavily overpainted. That's the red part here. Less so in the other panels, but the conclusion and the procedure was the same. Yeah, we remove all that. Yeah. Okay, I will skip this one. This is a video on how this works. We're moving on in time. I showed you a little bit how these XRF is useful for getting different types of information. But then came for us the second stage. So in the meantime, 10 years had passed. People started buying the scanner. All kinds of musea saw that was quite interesting. People like Marcia started to build their own instruments in some locations in the world. But what we could not really answer very well is answers from art conservators about chemical changes. What we started with, what was my original interest, to try and see and explain what happened at the surface. While we were doing all this scanning, what we also did on the basis of small samples was to take these small samples to synchrotron facilities and use all kinds of X-ray based spectroscopies to understand, to get some information on that, but always on the basis of very small samples where we hoped they would be representative for big paintings. For instance, we'll come back to that. In paintings of Van Gogh, you have cadmium yellow and also chromium yellow. Chromium, the chromate in chromium yellow is chromium 6. Sometimes, in a number of occasions, you see that this reduces to chromium 3. And this is actually the cause of this browning I was talking about in the beginning. You can see that very well by analyzing samples, small samples from, for instance, the sunflowers. Here in this flower piece, what happens is that cadmium sulfide becomes cadmium sulfate. We'll talk about that a little bit later. So you have all kinds of chemical transformations, sometimes complicated, different steps. And what we wanted to know then, due to light and photo corrosion of the pigments and things like that, and to explore this, what we were using usually were microbeam methods, where we use X-ray beams or electron beams or pixie beams, proton beams, around 1 micron, so that we could see the difference between those different layers. And occasionally we did use TEM methods to look at individual nanoparticles, but not too much. And then what I wanted to have at the macro level is the information that you get from the micro level, from more sophisticated methods than just elemental ones. And what we then started to do was to develop another kind of macro method, not Macro-XRF, with elemental maps as a result, but we started to do X-ray diffraction on the macro scale. Okay. And an occasion where we could use that is shown here. This is the inside view of the Gallery of Honor of the Rijksmuseum in Amsterdam. And in the Gallery of Honor, there are the most important works of art of the Dutch Republic, which was very rich in the 17th century. So I have a lot of paintings from that. And here, this big painting, it's called the Night Watch. It's the masterwork of Rembrandt. And if you look very carefully, you see some device in front, and a lot of people looking on what's happening there. Huh? And they are luckily shielded, let's say, from the instrument, and the instrument is shielded from the public via this house, glass house, which was built around. And the instrument that we use there, we built ourselves again, uses an X-ray beam. Where is our X-ray beam? Like this, there is an X-ray tube, and we shoot at one particular point somewhere here with a monochromatic beam, copper X-rays, and then we get these cones of diffracted radiation, and part of that we detect with this camera, which is sort of in front of the painting. Yeah? And it's really, everything is really smack against the painting, yeah? So 5 millimeter. So everything is there on one platform. We have our tube, we have our detector, and then we move the entire thing in X and Y in front of the painting without hitting it, obviously. Yeah. So that's our Micro-XRPD. Yeah, you see here the X-ray beam and then the diffracted cone. So normally in transmission mode, if you would shoot a beam through the painting and collect centrally around the beam, we would get these nicely concentric Debye-Scherer rings. But we're not doing that. We're doing reflection mode XRPD, so we get part of that. And these are not ellipses, but they're paraboloids, etc. But it doesn't really matter too much. You get the same information. You can get diffraction spectra in which you can recognize which peaks are there, and you can now recognize crystalline materials. You cannot no longer, as with Macro-XRF, say, oh, there is some lead there, but I cannot tell you what it is. Here you could say, it's a mixture of 3 carbonates of lead. Much more specific information, and therefore also more relevant information for when things start to change chemically on the surface. Yeah? So here we only have 3. In some cases, there are 5, 6, 8 different kinds of crystalline materials we can detect there on the surface. All kinds of other advantages to using this kind of coherent imaging or Rayleigh scattering-based imaging. And the energy stays the same. So all kinds of quantitative calculations on relative ratios are also much more easy. So what do we use this for? For instance, we can look here at this central part of the night watch. We're moving here, let's say, in 100 by 100 steps, X and Y. This means we're collecting 10,000 diffraction images, and we have 10,000 local compositions, a little bit much to look at one by one, but we can create maps. Now, no longer elemental maps, as with Micro-XRF. These are species-specific maps. We can look at calcium carbonate, and we look at lead carbonate, and at mercury sulfide, and at silicon dioxide, and some other stuff. Yeah? And all these here on the top, this was used by Rembrandt while painting. They are called primary materials. They are on his palette. But these two here, wedellite, which is a calcium oxalate, and palmerite, which is a lead potassium sulfate, they grew on the surface during this period of 400 years. They are secondary materials. And they're very interesting because you can see how the surface was altered. And then you can go wondering about, is this the same? Is this only here? Is this in other parts the same or less? What about other paintings of Rembrandt? What about other painters of the 17th century, etc. Yeah. So this opens up new avenues. You can see this here again. This is the central figure of the night watch, Captain Banning Cook. And we look at his face. Macro-XRF tells you there is mercury. The XRPT tells you that it is indeed a red pigment cinnabar. Here, calcium not in the face, but a lot around the hair and in the mustache, etc. There are actually 4 different calcium compounds, some primary, some secondary. Lead, 4 different ones. And you get a few extra, which are difficult to collect because they are based on silicon, and silicon X-rays are too low to really exit or pass through a lot of air. But with XRPD, we can see that there are a few silicon minerals there. Yeah? So more information. and also a little bit more acrobatics sometimes. So sometimes here our scanner was fairly low, and sometimes it was on a much bigger stage. It was being moved itself to reach the upper floors. So the Rijksmuseum, they have unlimited budget for this. They rent things and organize this. So this was also a bit fun in terms of organization and what we could do there. And so, yeah, for instance here, this Banningcock, we discovered that in the face, next to all these known compounds, very faintly, you see there that somewhere here there is lead formate. Nobody had seen before that this lead formate formed as a degradation product, but we saw it for the first time because we could do this mapping. And then by repeating this kind of aging process in the lab, we could indeed show that lead formate is formed when you combine some ingredients and give them energy. Yeah? And we had a nice paper on this in Antwerp, just saying, oh, look, in the night watch, for the first time, we found this lead formate. Okay. So this Macro-XRPD is useful for heritage science, art conservators, also to some extent for art historians. Why? Because you can sort of, by some of the secondary products and certainly the primary products, give you information on what the painter was doing exactly. And so, for instance, this lead formate is only formed when the paint which Rembrandt used was strongly alkaline. When it was regular paint, then you don't see the lead formate. So Rembrandt or somebody in the workshop of Rembrandt had to know that you had to add some alkaline products to the paint for some reason, and then you get this lead formate. And why did they do that? Well, they did that to adapt, modify the rheological properties of the paint. Paint is very strange. What you want is that if you dip your pencil in a paint, it moves with you. If you paint, it should move. And then when you stop painting, it should stay where it is. So it needs to move when you move, and then it stops. Not all materials do that. You need specific rheological properties. And we have this indication, or we think that with this lead formate, this is a kind of indicator that in this workshop of Rembrandt, they already knew what to do to change the rheological properties. Okay, it's a bit of an elaborate reasoning based on recipes and what we measure there, but that's why we do that. Very well. The last thing I wanted to tell you, let me see how far we are, is tell you a little story about this painting here, which is now, we switch historical periods, which is very well known, which is the Scream by Norwegian painter Edvard Munch. So, Marcia referred briefly in her introduction to the Mona Lisa. That's the most important painting of France. This Ghent Altarpiece is the most important painting in Belgium. Rembrandt's Night Watch, most important painting in Holland. This one, that's the Norwegians, their top, their Mona Lisa. Okay, so, and you see here again our Micro-XRPD scanner with two happy people. We sent that one, the machine and these two people, by ferry to Oslo, because this painting is in Oslo, in March of this year. And the reason why we wanted to look at that was actually to compare this version of the Scream to, of course you know the Scream, and emoji, etc., to the other Scream, which we analyzed before, 10 years ago, but also to a number of not so well-known companion paintings which Munch also made. Okay, I will not go into why exactly we were doing that, but let me tell you that the main yellow color here is cadmium sulfide, which was very popular in the time of Munch by other artists. Cadmium sulfide, as I told you already before, sometimes is a bit more orangey to red when there is more selenium. Can also be a bit more pale, and if you replace all the cadmium by zinc, you get something white. All right. But when you play around with this, do this band gap tuning, it's not so positive for the chemical stability. Cadmium sulfide on its own is very stable, always stays yellow, but if you tinker around with it too much, you destabilize it. Huh? More potential energy in the lattice, or whatever you want to call this. And so a long time ago, we started looking at this painting here by Ensor. In the corner, you see on the surface some white stuff which is growing, little crystals that have formed spontaneously, and not here in the corner. And the corner here was below the frame, so there was no light falling for about 100 years here, but on this part there was. So it had to do something with some photoactivation or photocorrosion. And yeah, we took a sample from this painting and did zanes, sulfur zanes at the IFUSP on this. And then in the sulfur, you see very clearly that there are these two peaks here, one corresponding to the sulfide states, that's here, and the big peak here corresponds to much more oxidized sulfur, so to cadmium sulfate. Yeah? And you see here this false color image. You have this kind of covering, bit of green, whipped cream, let's say, on top. Yeah? So there was surface oxidation, very simple chemical reaction. Okay, this was our first encounter with that, but as I said, it doesn't always happen. And we were left with the question, when does it happen? Or why does it happen? And why do some paintings do it and others not? Okay, now, of course, cadmium sulfide is very well known. You find this in batteries, you find it in solar cells. It's very useful. It converts energy, solar energy, to electron hole pairs, and then you can use either the electrons or the positive holes to do some interesting transformations for you. Very nice. This is a kind of physical view or a solar cell view. A more chemical view is that, yeah, both the electrons and the positive holes can do all kinds of other things too. Not what you want, but they do things. Eh? Like here, they can oxidize, the positive holes can oxidize the cadmium sulfide to cadmium sulfate. That's possible. And then, yeah, what happens is that this strong color is lost because cadmium sulfate doesn't have a color. It's not a semiconductor anymore. Yeah? And if this occurs partially, you get something pale yellow. And that is what you see. Yeah? And this is also what we found in the scream. Some parts here are, or a lot of parts are actually rather pale, where there is a lot of cadmium, while others are more strongly yellow still. And what we found also is that a reason or a kind of empirical association between the parts where the cadmium sulfide was degraded had lost most of its color, and this had to do with this cadmium compound, cadmium hydroxychloride. In small samples, which we analyzed, yeah, this was in the New York Times, etc. In small samples and by doing infrared analysis on tiny bits of paint taken from this very famous painting, what we found there are very tiny peaks which point to that everywhere where the cadmium sulfide was unstable, oxidized, we found this cadmium hydroxychloride there. Yeah? And when it was not there, there was no degradation. So empirically, we saw there is a relation between this oxidative process, this photocorrosion process, and the cadmium hydroxychloride. But nobody knew why. Huh? You can say, oh, there is a correlation, but there's not a cause. So we tried to figure this out, why this was, and we tried all kinds of stuff. Huh? And indeed, it was really there. We did chlorine zanes, and we found here, for instance, experimentally a very well-matching zane spectrum with this cadmium hydroxychloride. We used X-ray diffraction on the micro level, and indeed, this sample was full of cadmium hydroxychloride, etc. And so, yeah, no doubt that that was the culprit of the oxidation, but no cause. So and then we looked on the nano level in this paint to see whether there was, where the chlorine was in relation to the sulfur and the cadmium. They were very much together, all on the same locations on the nanoscale. But we did get X-ray diffraction signals from simple cadmium sulfide, simple cadmium hydroxychloride. So there was not a mystery mixture compound there, but they were very intimately mixed. Okay, still the problem was not solved, but we had another publication on this showing these very intimate mixtures. Then I turned a little bit in desperation to some colleagues I have in the physics department that are interested or doing DFT calculations. So I told them, we see these two things together and this destabilizes the cadmium sulfide. Come up with a reason why that is. And they did. Huh? So they had this model, atomic model, where you have layers of cadmium hydroxychloride attached to the lattice of cadmium sulfide. And they had to stretch a little bit this lattice to make these connections, but they did that. And so they were adding more and more layers here of cadmium hydroxychloride. And what happens then, if you imagine that in a nanoparticle of cadmium sulfide, you have creation of electron hole pairs here by photons falling in. What happens then is that if this is connected up on the atomic scale to cadmium hydroxychloride, it works as a kind of drain of electrons. You have a dipole across these layers, which sort of removes the electrons, pumps them over to water, which is on the other side. And so then here in the nanoparticle, these positive holes are left. And they oxidize the sulfur ions, the sulfidic ions. Yeah? So our original idea that we had this oxidation was elaborated upon a little bit, and this became a kind of transfer of electrons from water, creating hydrogen gas and oxidizing the... So by going further down to the atomic level and involving a bit more expertise, we could understand what we were seeing finally. Okay, so we started to believe more and more that our cadmium hydroxychloride was really the bad guy. Found a reason for that, we published about it. Finally, why are these people there? Or one of the useful things they did was to show with our XRPD scanner in the scream, in the face of the screaming man, that indeed there is cadmium hydroxychloride. Not only in these tiny samples, but a lot of it. Yeah? Because here, let's see, this is the purple. There are some small peaks. That's nice in one sample or in one position. But also, when we do a map across the face of the screaming man, indeed, we see here in gray, we see that there is a lot of that cadmium hydroxychloride there. Yeah? And it was not just some unrepresentative sampling we did. No, it's there. There was all kinds of other stuff there too. But this is for us an indication that indeed what we had as a hypothesis for the destabilizing nature or agent, destabilizing agent of the cadmium yellow is really there. And with that, I'm sort of ended my story. This is sort of the chemistry around that, which we found in different paintings. And this one I will skip. I didn't talk about that. And I will thank you for your attention. Yeah.
So the session is open for questions. Se vocês também quiserem falar em português, a gente pode traduzir.
Thank you for your seminar. I wonder if you could use that X-ray diffraction analysis to check for the pollution gases changing the color of the glasses used in the vitros in the churches. You think that could be possible to use that?
Yes. We already tried to do this diffraction mapping on some stained glass windows. And what we see there are usually things like syngenite, which is sodium, I think it's sodium, calcium, sulfate. It's a mixed sulfate. Think of calcium and sodium, but I'm not sure. So you see a number of precipitates, usually sulfates. And on a glass window, there is usually not another source, credible source for the sulfur than the air of SO2, SO3. We also see on a lot of paintings a lot of these sulfates. There, the situation is a bit more complicated because in some of the organic layers, there also you can have a lot of sulfur. So if you have to paint not with inorganic pigments, so these are particulate in nature themselves, but you have to, if you want to paint with organic molecules, you cannot just paint with them. First you need to fix them on some inorganic substrate. And a frequently used inorganic substrate is alum, which is aluminium sulfate. So when something has been painted with transparent red layers, usually in that layer already there is a lot of sulfates. And they tend to move to the surface and then crystallize. So you get a lot of sulfate crusts on old paintings. And those we can see very well, also with diffraction. And if you only do XRF with that, they skip below the radar. Because, you see some patches of sulfur and calcium, but normally you don't get to the specific sulfates that are present. So we're discovering a lot of these sulfates everywhere now. Yeah.
Further questions? Claro.
Eu queria saber se eles trabalham, normalmente quando vão pegar esse trabalho, se tem algum relatório de restauro, alguma coisa para poder isolar, sabe, o que é a restauração e o que é o original, ou se isso vem na própria análise deles, sabe?
He asked if during this work, if you have some restoration report in order to separate what is
what is original,
what has been done
not.
and what has been not.
Yeah. Sometimes if the previous restorations have been done not so long ago, and therefore, let's say in the 1970s or so, in those cases there are indeed restoration reports. And then indeed you can match up, let's say when you find some strange compounds, that to a restoration intervention. But usually, especially when rather famous paintings are concerned, a restoration from the 1970s is then the fifth or so, and there were many more, which are generally undocumented. And so, for instance, in one of the paintings I showed you, the Ghent Altarpiece, there is a lot of green, because there are a lot of lawns. And so we know that while this painting originates from the 15th century, it was strongly invasively restored in the 16th century in Antwerp. And then in that century, they used a very particular copper sulfate, which was only used in the 16th century. And we found it back. And then we're in a lucky situation, because then we can really say without any doubt to the restorers, this needs to go, because it's not original. But we're not always so lucky. So but there are other interesting things that we can help. But restorers still have many questions. In some cases, we can really clarify their doubts, but not always.
Further questions? Yes.
Thank you for your talk. When you show the Francisco de Goya portrait, you were able to see the vermilion and the white lead in the underlayer painting.
Yes.
But in the surface painting, you also had some regions with red pigments and white pigments.
Yeah.
Were they the same pigments, or did you do some treatment in your spectra so you could deduce the pigment?
You're asking about the Dept selectivity of Micro-XRF. Well, no. Micro-XRF is not Dept selective, at least not in the sense. So what we could see there was this civilian, and then the general's uniform below. What was overlapped and what we could not resolve were the two faces, because the faces of the general and the face of the civilian were both painted with lead white, and you cannot then distinguish between the two. That's a problem. In many cases, it's not a practical problem, but let's say in principle, it's a problem. For lead, there is a possibility, because as you know, you have the lead M line and the lead L line. The lead L samples the material much deeper than the lead M. So you can play with that, but that's about the only thing you can do. What we did notice is that by moving over from the X-ray fluorescence to the diffraction, there, in a number of cases, when you do diffraction in transmission mode, by looking at subtle shifts of the diffraction lines, you can make the distinction. So you have a painting, you shoot through it, the detector that collects the diffraction cones is at a certain distance, of course, which is typically 10, 15 centimeters. If you would move that detector away, of course, your diffraction cones would have a bigger footprint on the detector. So this means if a signal from one layer originates from one layer or from a bit deeper layer, there is a small shift. And sometimes you can really use that shift to distinguish between different layers. But it doesn't really work so well. The depth resolution is so-so. But with fluorescence, it's not possible. You have to use other strategies, confocal XRF, something like that. Not too many people have done that. There are a few groups in the world that do it. In the Louvre, they have a machine that can do that. Yeah. You lose so much in flux and intensity that I've never bothered to go in that direction. Yeah. I mean, at a synchrotron you can do this, but not with a normal X-ray tube. This confocal setup where you, with the second polycapillary lens, sort of select from which depth you detect the signals is too selective. It's too inefficient, that step. So that's a real problem, yeah. Or limitation of Micro-XRF.
Further questions? I have myself. So in the virtual restoration, how the museums are embracing this technique in the sense of...
to what extent is this embraced, you mean?
Yeah.
Oh, in a qualitative sense, it's fine. Eh? People like that it helps them a little bit to imagine what the original painting may have looked like, but never in the quantitative sense. Because the moment people know, oh, we can have an idea that this layer looked different, yeah, they want to know, did it really look that way, or was it a little bit more blue, or was it a little more, and I think I always thought that it was actually blue-green rather than that. Then I tell them, you know what you need to do? You have to, now that you know in a qualitative sense how it looked like, start recreating this paint in the lab until you know that this variation corresponds to that color. So this, let's say, this transfer function from a paint composition to a specific color, it's not there in its generality. There is no model for that, so people need to do a lot of work in the lab. But this is regularly done by people really interested to recreate this. But yeah, it's not really something we've gone into. There's a lot of other people that can do that kind of exercises.
Great.
Yeah.
Further questions? Yes, please, Marcia.
First of all, I want to thank you very much for this talk. I understand that it's a very difficult test to perform instrumentation, to develop instrumentation. And you show us that when you apply this non-destructive instrumentation, you can have a better understanding of the material, like you show us, because here you can not take a sample, but also has a map or a big vision of this analysis. And then I want to ask you what's the difficult to develop instrumentation or combine instrumentation.
What's the difficulty? Well, how shall I say? Well, there are different levels. I always thought that we were always very lucky, in the sense that when we finally did a few of these tests with Micro-XRF at synchrotrons, that we were able, let's say, that we were permitted by nature and by what you could buy in terms of X-ray tubes and X-ray detectors, by just buying things and combining that it worked. We might have been able, by combining all kinds of components, arrive at something which was terribly slow or that burnt the paintings too much. So we ended up almost without any effort in a kind of window where the stakeholders from the museum liked it. I mean, this was years and years they asked, does it burn the painting? What happens? Can you explain? How can you prove that it's not? Now they don't ask anymore because they know their colleagues have this machine already and they're using it. So this has become clear and still is fast enough to, within a reasonable time frame, give results for Macro-XRF. Of course, in this world, in the museum world and the imaging, you have other methods, hyperspectral imaging methods with cameras, which are much faster. They are our competitors, or they are the competitors for the Macro-XRF. We are lucky that we are much more straightforward. We produce data blocks which are much more straightforward to interpret within the limitations of the method. With hyperspectral methods, you need to be an expert to extract information. So this saves us a little bit, but the time requirements don't help us. The Macro-XRF is slow. Then this one here is even slower. It's 10 times slower. So that's really a killer. There are many benefits, and we try to show the rest of the world what the benefits are. That's why I'm doing this here. But still, this takes forever. This little map I showed you of the head, it's not an accident that we only collected the map of the head and some other maps, not the entire painting, because it takes far too long. And yeah, this is a special painting. They want it on display all the time. We only had it for a few days behind the scenes. But that's really the killer. Yeah, here nature is not, or the offered components is not so generous, you could say. Why is that? Well, to be able to do this diffraction, we needed X-rays, of course, but they must be monochromatic and they must be parallel. And these are extra requirements, which makes that the flux is much more lower, and therefore we have to measure much longer. Yeah. Maybe by relaxing some of these things, you can make it go faster. Well, I suppose you can make it go faster at the expense of the 2 theta resolution in the diffraction. If you have a beam which is a bit less parallel, where you not take away all the photons that come out of the X-ray tube, but maybe with the same energy, but with a higher angular spread, you may still be able to collect X-ray diffraction data that are sort of interpretable. But yeah, we like these because they are rather sharp. There are other groups that also have made Micro-XRPD. Paolo Romano in Catania has done that. They're not happy because they tell us, how many compounds do you see? We never see all these things. But their spectra are not so, in the 2 theta range, are not so good. Yeah. So yeah, we have gotten a little bit stuck there. And maybe there should be some new X-ray optics, which is much more efficient, and that we're waiting for to be created. But that's not our expertise, yeah, unfortunately.
Great. So let's thank again our speaker.